Ladies and gentlemen, welcome to Ryan the Ride Mechanic channel. I am Ryan the Ride Mechanic. Thank you so much for showing up. I really appreciate it. And today I wanted to go over a few things, so I'm excited today to be doing the final video, I think it's the final video at least, on the linear drive segment. So I've already talked about brakes, I've talked about linear inductive motors, and today I want to talk about linear synchronous motors. I know a lot of people have been waiting for this one, have been asking about it with tons of questions. I've been like, there's a video coming, I promise, there's a video coming, there's a video coming. Here it is, the video is here today, so yay, we finally made it. So we're going to talk about linear synchronous motors today, or LSM motors today, and because the channel's still small, not a lot of people know about it, so please share it out there before they find out. And you know who I'm talking about, they, right? The people that are like, we want to talk to you about your car's extended warranty. Oh my God, they found us! Run!
Now get ready, here we go.
Seriously though, thank you so much for joining the channel. I really appreciate all the views and all the comments and what everybody does. It's awesome. Thank you so much for showing up to another video and watching. I appreciate that. And we're going to get right into it. Here we go. First of all, look at you. Thank you so much for showing up to watch another one of my videos. I appreciate it. Like I've been saying, this is knowledge that you can't really get anywhere else. I've learned it from working on these machines. I've learned it from talking with the techs of people that install the stuff, the manufacturers who built it, and even some of the doctors who design part of the engineering and the system that build and run these things. Sorry, a little bit tongue-tied here. Not reading my notes. Brand new teleprompter. No, I'm just kidding. I still haven't gotten the teleprompter. Still just bullet points on paper, but I'm working on it. I'm trying to. Okay, so I had a lot of positive review on the last one, so I'm going to start off with a little bit of history again. LSM technology first popped up in 1997 on, let me rephrase that, on amusement rides, roller coasters. First popped up in 1997 when Intamin built two rides, kind of the same, but kind of not. One was Superman the Escape that went to Magic Mountain, and the other one was Tower of Terror at Dream World. Got it. Anyways, both of the rides were launch style linear synchronous motors. They were the first of their kinds to come out, and Intamin built two of them back to back with each other. Fun fact that most people don't know, Superman the Escape from Krypton was installed. 1997 was the date, the year it opened, I believe, but it was installed before that. From the guys who actually did some of the commissioning and putting the thing together, they told me, they said, you know, it was put in, but when they actually turned the system on, they said it actually took 9 months to actually get the train just to move forward. I should say coach for that ride, but it took 9 months just to get the coach to move forward, let alone accelerate up to speed. But then once they got it, they were able to get it up and running, and then it's able to go all the way up to 100 miles per hour, which is pretty impressive. 100 miles per hour. So when the LSM rides were first introduced, they actually flopped pretty hard because the technology was actually behind the LSM curve. So they came up with the linear synchronous motor technology, and they tried putting it out there, but the rest of the industry still wasn't ready to utilize this drive. So the communication wasn't quite right back and forth between the motors and the drive, and there was all sorts of other problems that they just really hadn't ironed out there. Was it anyone's problem? No, not really. It's just what happens when you release things ahead of their time. You get all sorts of headaches and stuff that goes along with it. I heard a lot of the problems that were original with these rides were mainly revolved around the Hall effect sensors. And the Hall effect sensors measure basically the magnetic intensity underneath the train as it passes by. So I had a lot of problems with those, and of course when those sensors fell out of alignment or out of calibration, it would cause the drive to do all sorts of weird things, which would include breaking components all over the place. And I know I've talked with plenty of people and said, well, yeah, sometimes Superman, the Escape, they said, oh yeah, one side's always down. That's because it's so hard to maintain. They were taking parts from one side to fix the other side and vice versa. You have to cannibalize the ride kind of to keep it up and running, because the parts were brand new. It was hard to get a hold of and everything, and it wasn't a great situation all the way around. But you kind of get what you get when you have prototype rides. They can either make or break a park. It's quite amazing. So after these LSM rides came out, it was kind of a headache, and the manufacturers, parks in general, didn't really want to go down that road yet. So they turned to the earlier released LIM, linear inductive motors. They turned to those style launch rides and said, well, this is a little more stable, even though they consume a ton of power and they have all sorts of other issues with them. But it was looked at, the LIM was the most stable thing to put into a park, and so they started building much more LIM rides at the time. The LSMs, don't get me wrong, they still ate up a ton of power, but the idea, the fundamental of it was going to be way better than LIM ever could be. So it was very intriguing for a lot of people. That's why it never phased out of the industry. Over time, the LSM technology came up and surpassed the LIM technology. And then LSM started to be used in everything, not only launch roller coasters, but they started to be using for positioning. They started to be used for lift hills and all sorts of other little things around the place. So lift hill is a big one because you can build a lift hill that's only 100 feet high and actually accelerate the train up the lift hill and get it to the speed coming down off the backside like it was a 200-foot drop. So you could advertise it as a space-saving idea, which is really interesting to think about. It's like, oh yeah, build a lift hill, but make it a smaller lift hill. That we can still give people a little bit of anticipation of heading up there and then launched over the top, kind of like a lightning rod or something like that. LSM stands for Linear Synchronous Motors, and the main difference from LIM to LSM is that the train is fixed with permanent earth magnets underneath there, just like the magnets that were used in eddy current brakes. These are the exact same eddy current style brake magnets underneath there. They have the big square block neodymium magnets with opposite poles facing each other. So that's to get the polarities across the LSM correctly as it goes down the track. Much like the LIM motors, the LSM motors also use windings vertically inside of a stator that's built together. There are 6 of them, just like an LIM, but instead of an LIM where the windings, I'll go back to these guys again, where the windings are put in front of each other, like this, to make a stator, these windings are now side by side with each other. So now they're in line like this. So you now have 6 sets of windings going this way, and the train is now passing this way. So they're right next to each other just like that. These windings, just like the LIM. In the LSMs, they're a little squished. Let's see if I could squish one here. Nope, it's too strong. But these are squished. They're not so much round in this case. They're more oval inside the motors. I didn't have a picture. I took a picture a long time ago. It was kind of interesting to see. But on the side of the LSMs that were lining the station, midway through operation, I took a picture with a thermal gun, an infrared FLIR camera, and you were able to perfectly see the little, they almost look rectangular coils on the inside or windings on the inside all the way down the stators, and you're able to see how hot they were going all the way down. We were having cooling issues with the ride, so we wanted to see if there was hot spots inside the motor. But those are solid cast motors. They're the same type as the LIM. They're resin bound on the inside, and so this is encased essentially in, we'll just say it, an epoxy. They're inside epoxy and with an iron core in the center, and they're completely sealed. You can't get to them at all. The ones I was dealing with were not serviceable, which means you can't take them apart and work on them. But I noticed a lot of the ones that I believe Intamin's using right now, they look like they can be taken apart. looks like there's the casing on the outside is held together somehow. So I wonder what that's all about. Honestly, I don't know. Gotta say this, we'll go. These are LIM like this, where they're right in front of each other, and the train would be passing towards me. And then these are LSM when they're in line with each other like that. Same thing, train passing this way. These stators lining the track can be used either side by side with each other or in line with each other. It just depends on the type of ride that you're doing. If you're able to put two stators side by side, you can get much more forceful acceleration, but most of these days are being used, they're just single file in line with each other. Unlike LIM motors, one stator by itself can also be a motor by itself. The drive actually determines the amount of stators it wants to put together for a motor, which is predetermined. It's not something it figures out when it launches the train. It's predetermined, but between the stators on the track, you're going to see these small, they look like smaller stators, very thin. A normal stator is about a meter or a little bit longer, and these look like a very small stator. They only appear to be about this big, 5-6 inches, somewhere right around that area. They're very small. Those, like the linear induction motors, they used optical net sensors to get feedback of the train. These smaller stators that are in between, these are called tail sensors, and these are the Hall effect sensors that were problematic at the beginning of the LSM life cycle. These are the Hall effect sensors that are now in line with the motors. The train passes right over them. And those Hall effect sensors will determine where the train is exactly, which way it's going, and how fast it's going. And then it will also determine the polarity of the magnets passing over it, which gives the rake signal back to the drive that allows it to figure out a pulse to how fast to fire the motors. I'll give you a little demonstration of how one of these tail sensors is kind of set up on the inside using my sophisticated technology again that everyone's been asking for since the first time they see it. Here we go. Drawing stuff on paper again. It's awesome. Absolutely awesome. So this is essentially a tail sensor right here. It is made up of, let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's made up of 8 sensors that can read magnetic polarity. And what they do is they use 4 sensors on the outside. 1, 2, 3, 4. Those just determine that a magnet is over it, and those are basically used to enable the sensor so you don't get erroneous readings. So once all 4 of these sensors go high, it activates the 4 sensors on the inside. And if you notice, there's a north polarity sensor and a south polarity sensor, kind of like this. And those measure the magnets as they pass by. When the magnet passes by and it's a south, it comes to this first one. This one does not turn on, but this one does as it passes by. Now you got to remember, just like we've said in other videos, just because there's the south passing by here means there's a north passing by here. So there are 2 more sensors on the back side. Again, a north and a south. North and south, north and south. That means as you have both polarities, a north and a south, pass by, that rake sensor can pick up both at the same time and tell the drive not only that, hey, the train's going that way, but it's able to say that I have a north polarity magnet right in front of me on this side, and I have a south polarity magnet right in front of me on this side, and then it's able to determine how fast it's going by when these other magnets when these other sensors activate on there. So that's the tail sensor. So that's the critical feedback, the tachometer, the speed, everything. That's the important little guy to look at on the track. Just like any inductive or synchronous drive system, when the ride turns on, it does not know where its train is, so it has to find the train. So when you start the ride up, it goes into a hunt. And as you see the train on the track, you'll hear the motors start to fire. Let's say the train's here, right? you'll hear the motors start to fire and they'll start walking their way up this way towards the train. When the train gets it, it starts pushing that train forward until it's out of the tail sensor that it was on, because tail sensors are always the length of the train apart from each other. So once it moves that train out of the tail sensor into the next tail sensor, it finds the head of the train. At that point it says, okay, I know where the train is. And then the drive stops and reverses it, and then it brings it backwards. Now if it pushed it away from the station the first time, it'll bring it back into it the second time. But the ride has to find the beginning of that train each time, so it knows where it is. Sometimes it's able to do it from the station, and as the train dispatches out, it's able to find it and say, okay, there it goes. But the drive needs to know where the train is and turn on and move it the first time. Motor synchronization out on the track is a pretty complex subject for this one, because it involves lots of polarity of magnets and then lots of windings generating magnetic fields at the same time. So I'm going to use a couple other visual aids on this one to show you. So for this, we're just going to do some basic diagrams. We're going to make it easy for everybody to understand. This right here is a magnet. It looks like a post-it note, but it's a magnet. You're going to have to trust me on this one. Alright, so this magnet's polarity is north. Got it? Remember magnets, what happens? Opposites attract to each other. The ones that are the same, if I put two norths next to each other, they repel each other, right? So, on the track, if my magnet is coming this way, I have right here, stator, south. So as my north magnet comes here, this stator turns on and then attracts this over it. At that point, as this north magnet gets to here, this stator now has to turn off. And this magnet has to coast over the center of that stator, and then it's going to turn on another stator, well, it's going to turn on the same stator, I should say, in the north polarity, and then push this away. Make sense? Okay, so we have, sorry for the audio there. We have an attraction, and then as it gets right up to the stator turns off, goes over the stator, and then turns back on in the opposite polarity, pushes the magnet away. So we have opposite, neutral, and then the same polarity to push it out. Now because of this, you have windings doing this. And the windings internally inside the stator will do this number. They will constantly flip-flop with each other. So what you're going to have is you'll have this. If I take the windings the way they're set right now, I have a south and a north, and then I take my north and put it right in the middle of the two. Which way is the train going to go? Well, the train's going to go this way because it's attracted to this one, it's repelled from that one. So the train goes that way. If I swap the polarity on the stators like this, put my magnet in the center, now the train's going to go that way. This is the basic principle behind linear synchronous drives, is that it's all based on magnetism and polarity. Pushing and pulling, pushing and pulling, pushing and pulling. Alright, so I made another diagram. We'll just do this. We'll say this is the magnetic shoe on the bottom of the train. A north, a south, and a north magnet. And this is the train passing by. Well, I've got my stator right here, so I'm going to energize my stator right here, and then it's going to attract right over it. Put it into neutral, and then turn it on again once it gets a little bit past. So you see I have them lined up like that. So right now this would be the train if I were to slow the train down and fire the stators like this would just lock right here. The train wouldn't go forward or backward. But because the way everything is sequenced, we put it just slightly ahead, and now the train wants to go this way. But you gotta remember, that's not that forceful by itself, but that bottom of that train has what? It's got a whole nother side of magnets to it, right? And that's okay, because that stator that's in there also has a different set of polarities to it. So every time you do this, you actually do this. Man, I hope that's lined up right. Every time you fire a stator off, you're actually doing all these different transactions inside there to get the train to move forward or backward depending on where it is inside the stator. Now, for this reason, because you have all these magnets working together off all these polarities, that's the reason that linear synchronous drives can produce a very high amount of torque and a very little loss, which means that as it pushes forward, it's able to push the entire train forward and not lose it like it would on an inductive style motor. So synchronous motors are very torquey, but they also demand fine control because of that, because the signal can't pass up those magnets, otherwise it goes the opposite direction. So because of all these components working together in a very fine amount of space and very quickly, one of the main reasons that the original Hall effect sensors had such trouble is because they were wired in. And all these new tail sensors, they all use fiber optic communication. So it really wasn't until the industry got fiber optics down to a cheaper, more obtainable level for most people to use, did these things start working better and more effectively. How fast the train accelerates is depending on how much current and what frequency that they could rotate the magnetic polarity at going down the track. Since LAM motors put that frequency out there very fast and down the entire length of those motors, they can move one direction with much loss, but they can do it fairly quickly. So for spacing the stators and windings further apart to make the train accelerate faster, it just becomes more complex because everything has to move a lot quicker. Since how fast everything communicates is an issue on these rides, connected by fiber optic and other things, it is essential that an LSM drive be located close to all the launch areas of the ride. So you wouldn't want to have LSMs way out on one side of the ride and the drive control cabinet way out on the other side of the ride, because the communication path would slow down and there might be a lag in signal, which wouldn't be good for the ride. Okay, so we've talked about LSMs, we've talked about acceleration. Let's slow it back down, literally. The preferred method to slow an LSM ride down is to simply ground the stator out. When you ground a stator, the LSM turns into a giant alternator. If you've ever tried to turn an alternator with it connected to the load source, it's very, very hard to do. If you actually ground a stator out as the train is passing over it, it will literally blow the windings out of the stator. Therefore, we need to choke grounding down. So in that case, we use what's called a brake resistor. Just like a resistor on an electronic piece of equipment, it resists the amount of current going through it. So instead of putting, let's say, 200 amps to ground, you put that resistor in the way and it only allows 75 amps to ground. And you can use different size brake resistors for different areas, which you have to in order to deal with the different size stators putting out different current. Back in the control room, there's a large bank of resistors used to simulate grounding out the stators on the track to earth. The braking resistors are wired in to be what's considered normally closed or always on. So when a e-stop is triggered or under a power failure, the resistors will naturally connect to the stators with no extra force, and whatever power is being generated by the train will be naturally dissipated through the stators, through the brake resistors, down to earth. And that will cause the train to come to a very quick stop out on the track. So under normal operation, the braking resistors can be used like on and off, but they can also be used in little waves as the train passes over it. So when a train is coming in to the final brake run and slowing back down, they might choose to put the resistors all the way on and scrub the majority of the speed of that train off, but then as the train starts to slow down, they might start pulsing those resistors on and off, on and off, on and off, to take that slowdown curve and gradually level it out down at the bottom, so the train has a nice smooth transition, or maybe then stop it and let the train just roll off the stators on their own to go to the next area of the track. So let's talk about the drive real quick. The drive is very, very, very similar to an LIM drive, just smaller, because LSMs are more efficient, so they don't need as much current and power. So in this case, the one I was working on, we took the 13 kV, 13 kV of the incoming power to the park, put it into a transformer, and stepped it down to 690 volts at about 1000 amps, right around there. That was the service coming out of it, I believe. And then from there, we brought it into the control room. Once the power came into the control room, it went through the drive, and the drive was able to break it back down from AC into DC and store it at 1000 volts on the bus. And then it was able to reorganize that signal through its IGBTs and then put the AC wave back out into the track on the stators. But remember, it's not an AC wave, it's actually more along the lines of a square wave DC, because the ride knows exactly what it's firing, positive or negative, at what voltage, at what amperage, to what stator, at what point in time, and for how long. Again, really complicated. Just like the LIM drive, the 1000 volts is placed onto a bus, and that is distributed out to the thyristors, and the thyristors are the on-off switches that guard the stators. So just like LIM rides, you don't want stators firing with nothing above it, because you'll probably damage the windings and prematurely fail the stator out on the track. Current consumption on an LSM ride is much, much lower, because on this ride that I was dealing with in particular, it was running off of 690 volts, and it would only pull up about 900 amps on a full launch. So it was very small compared to 500 volts at 5000 amps on the LIM ride. I think that's going to do it for me. Please like and subscribe. Let me know you enjoyed the video, and take it easy. Bye-bye.